Imagine a ball covered in hair. The hairy ball theorem proves it is mathematically impossible to comb it completely flat without leaving at least one tuft, swirl, or cowlick.
Wait, is this a deep geometry thing, or just because hair is physically thick?
In topology, we treat each hair as a tangent vector at a point P. If the hair is combed flat, it stays tangent to the surface. Together, these form a continuous tangent vector field. What if we try to push all the hairs in one direction, like following the lines of longitude from the North Pole to the South? Can we find a smooth combing that works everywhere? Try a simple strategy: combing hair along longitude lines from north to south. It looks smooth at the equator, but look at the poles. Vectors from every direction converge at a single point.
Wait, if they all meet at the top, which way is the hair actually pointing?
The answer is, it can't point anywhere. For the field to be continuous, the vector's length must shrink to 0 at the pole. This creates a singularity, or what we call a cowlick. No matter how you swirl the field, you can't escape this trap. The hairy ball theorem formally proves this. Any continuous tangent vector field on a sphere must have at least one point where the vector is 0. It is a mathematical certainty dictated by the sphere's topology. This isn't just abstract math. Consider the wind on Earth. Because our planet is a sphere, the hairy ball theorem guarantees there is always at least one point where the horizontal wind is exactly 0. That is often the eye of a cyclone.
Wait, so is that why cyclones have an eye where everything is calm?
But look at a torus, or a donut shape. Here we can comb the field perfectly. The vectors flow around the hole and through the body without ever reaching a 0 point or creating a cowlick. The difference is the Euler characteristic, chi. For a sphere, chi is 2, forcing a singularity. For a torus, chi is 0. The sum of the indices of the zeros must equal chi. This topological constant dictates what physics allows. Topology isn't just about shapes. It's about the deep rules that govern the physics of our universe. Whether it's wind on a planet or fluid in a lab, the holes in the geometry define what is physically possible.